Hi, this is Dr. Emenacker. In this particular video, we are going to look at ways of evaluating limits algebraically. Now, there are some limitations as to when you can use this technique, and we're going to take a look and discuss that as well. And then we're going to go into 6 properties that are useful for evaluating limits. First off, when can we use these things? Well, it's not uncommon to, if you're working with a function, let's say f of x, equals, let's say 2x plus 4, okay, have a function that's continuous. By continuous, what I mean is if we were to graph this function, slope of 2 goes to the y-intercept at 4, the graph might look something kind of like this. Continuous meaning I can draw a picture of it without having to lift my pen at any point. There are no breaks, there are no gaps, it just keeps going. It doesn't necessarily mean that it has to be a straight line. A function can be continuous and have all kinds of curves in it, okay? It just doesn't have any gaps or breaks in it. So what's going to wind up happening here is as we're working with these various properties, we're going to primarily focus on functions that are continuous. Now, if we have something that's continuous like this, we could do this limit as, let's say, x approaches -1 of the 2x plus 4. And because the function is continuous, it is perfectly legal to just substitute in the value of x that we want to evaluate at. And what winds up being the case is as x approaches a value of -1, the limit, the y value, approaches a value of 2. If we look at this graph, let's say right about here is -1. If we're coming at -1 from either the left hand or the right hand side, remember a limit like this without any exponential notation of a plus or a minus means you're coming in from both sides. So if we come in from either the left or the right hand side, in either case, we're headed toward a y value of 2. Okay, so with that in mind, let's take a look at these properties that we're going to find useful for a good deal of time. Okay, the first of these is how do we handle limits when the function is a constant? Okay, so the first thing we're going to look at here is what do you do when the function is a constant? So let's say we have something like g of x equals 4. If you'll recall, with a function like this, regardless what value you plug in, the y value that will come out will always be 4. Okay, so if we evaluate the limit as x approaches some number, okay, and I'll just call this some number a of the function 4, doesn't matter what the value is that I'm going to wind up plugging in for x. Notice in the function there's no place to take and plug that value in. We're always going to get back the value 4. So what the first property says is if we do the limit as x approaches a of c, we will get back c. Now there are 2 things we need to note here. A and c are both real numbers. Okay? They don't have any variable in them, just like what we've seen here. Okay, the function is 4. We could change that up and we could say, well, the limit as x approaches -2 of 7/2 equals, and in this case, notice both the value that x is approaching and the function, both of these are constants. Okay, and what you'll wind up with here, doesn't matter what value of x we're working with, you will always get back 7/2. Now remember, constants don't always just look like a number. Let's say x approaches 7 of pi. Pi is a number as well. Doesn't matter what value of x we use. If we graph this function, it's going to be a horizontal line. And that horizontal line is going to cross the y-axis at the value pi. So regardless what value we substitute in for x, we will always get back pi. Okay, so this first one, the thing to be mindful of is the value that we have for the function. Could be something kind of strange like pi, could be something as simple as 4, or a little complicated like 7/2. Okay, but it doesn't matter as long as that value is a constant, constant meaning it doesn't change. The limit at any value of x will always wind up being the value of that function. Second thing here in the top left corner is let's take a look at limits when two functions are added. Okay, so first thing we're going to do is I'm going to create two functions. Let's say we have something like f of x equals 2x plus 3, and we have g of x, which is equal to x squared minus 1. If we were to compute the limit, and I'm just going to pick some value for x, doesn't matter what the value is, we'll keep it simple. Let's do 4. The limit of f of x plus g of x, where the limit's applied to the sum of those two functions, is going to be equal to the limit of f of x as x approaches 4 plus the limit of g of x also as x approaches 4. Using the values that we have here for these two different functions, what this essentially says is we can do the limit as x approaches 4 of 2x plus 3 plus the limit as x approaches 4 of x squared minus 1. As we talked about at the start of this video, if you have a continuous function, the first of these functions is a line, continuous. The second is a parabola, also continuous. To evaluate the limit, all you need to do is to substitute in the value 4 for your limit. And what we're going to have is 2 times 4 plus 3. That'll be the value of the limit from the first portion, plus, then we're going to have 4 squared minus 1, the resulting value from the second limit. And what this is going to give us is 11 plus 15, which is 26. When you have two functions being added together, in essence what this says is you can just do each function separately, get a value for it, and then add the resulting values together. The third property that we're going to look at, and is now listed in the upper left corner, is limits when two functions are multiplied. You may already have an idea of how this is going to be handled. Okay, so let's say we have two functions. Let's say we have f of x equals 2x plus 3. And let's say we have g of x is equal to x squared minus 1. If we do the limit as x approaches 4 of f of x times g of x, this can be evaluated by actually doing each limit separately. And then multiply the result from each of the two limits together, and it'll give you the resulting value. So in this case, this could be solved or evaluated by first doing the limit of f of x. So that's going to be 2 times 4, because x is approaching 4, plus 3, times Remember, this first part is from the limit f of x times the limit g of x. That's going to give us this 4 squared minus 1, like that. And we can evaluate these, and we're going to have 11 times 15, which is 165. Okay, so when you have two functions being multiplied together within a limit, it is fair game to do the evaluation as two separate smaller pieces, taking the result from each of the smaller pieces, multiply it together, and in the end bring it together to get your final answer. Okay, number 4 on the list, limits when a function is multiplied by a constant. Okay, something like this would look like the following. Let's say that we have f of x equals, let's stick with this 2x plus 3, and we want to compute the limit of, let's use a number that isn't going to be involved in the problem, 5 times f of x as x approaches 4. This can be evaluated as 5 times the limit of f of x as x approaches 4. The reason you can bring the 5 out in front of the limit is because the 5 is a constant. It is not dependent on the value of x, so it's going to have the same effect regardless what x value we're working with. In this case, this can be evaluated as 5 times the limit as x approaches 4 of our function, in this case 2x plus 3, which is going to be 5 times, we're going to substitute 4 in for x in our function, which is going to give us 5 times 11, which is 55. Okay, so there's an application of the fourth property on our list. If we go back up and check what's going on, let's see here. Number 5 on our list, now in the upper left corner, is a limit when one function is divided by another function. Okay, so this is going to look something like the following. An example of this would look like, let's say we have f of x equals, let's stick with our 2x plus 3, and we'll stick with g of x equaling x squared minus 1. Now what we can look at is, what do you get if we do the limit as x approaches 4? I continue to use 4 throughout this because there aren't any 4s anywhere else in the problem, but you could use any number you want. Okay, it could be a square root of 17, could be 8, could be negative 24. Okay, so realize we're not just limited to 4. I'm just sticking with 4 because 4 is not a value in either of the two functions. To evaluate this, what we can do is to rewrite this as the limit as x approaches 4 of f of x divided by the limit as x approaches 4 of g of x. Okay. Now we're going to assume here that the limit in the denominator is not going to 0. If it was, we've got a problem. We've got an undefined function. Okay. So to evaluate this, it's going to be the limit as x approaches 4 of this 2x plus 3 divided by the limit as x approaches 4 of the x squared minus 1. Substituting in the value 4 for the x, we have 2 times 4 plus 3 divided by, here we're going to substitute in the 4, square it, minus 1. And when we work this out, 2 times 4 is 8 plus 3 is 11. We're going to get 11 over 15. And that would be our final answer here. Now you might be thinking, well, gosh, that's not like answers I got in algebra. They were always nice. That's true. It's not like answers you got in algebra, but we're not in algebra now. We're in calculus. So you need to become accustomed to seeing results that aren't always so pretty. Okay. So remember, a fifth property says that if you have one function divided by another, you can evaluate each of those two separately, and in the end, take the result from the numerator divided by the result from the denominator. The sixth property that we're going to look at addresses situations where you have a function raised to a power. So for example, let's say we're going to continue to use our f of x equal to 2x plus 3. And let's say we had something like the limit as x approaches 4 of f of x squared. Now it doesn't have to be squared. It could be cubed, could be to the fifth, could be to the negative 2. Doesn't matter what the exponent is. What you wind up doing is you first evaluate your function. So what I'm going to do is I'm going to do the limit of 2, substitute in 4 for x, plus 3. Okay, actually I don't need the limit there. And then after I've evaluated that, I'm going to square it. This is going to give us 11, 8 plus 3 is 11 squared, which is 121. So when you wind up with a function where you have an exponent in it, it's absolutely fine to just go ahead, evaluate the limit, and apply the function or the exponent to the function thereafter. Each of these properties I've given you an example of, but each of them comes with a more formal definition. Let's take a look at those more formal definitions at this point. Okay, let's say that we have the limit as x approaches a of f of x. So I'm not restricting myself to x equaling 4 or something like that, is L. Whatever the function is, and we substitute in whatever the a value is, we get back this number L. L could be 2, could be negative 7, could be the square root of 19. Who knows what it is? It'll vary with the function and the value that x is going toward. Let's work with a second limit as well. This one, the x value is going to be approaching the same value a, but our function's different. So since it's different, we can very likely be headed toward a second number. Okay. So defining these two limits like this, let's go back and do a little more formal or a little more abstract definition for each of the 6 properties we just looked at. The first one talked about the limit as x approaches a of some constant. Now I want to put down up here that a and c are real numbers. So there's a third thing I want to state up there with my conditions. It's going to give you back c, which is what we saw earlier. The second property dealt with a situation where you have two functions being added together. So if you have f of x plus g of x. What's going to wind up happening here, if you'll recall, we first evaluated the limit with respect to f of x, and we got L. Then we evaluated the limit of g of x, and we get M. So if you have two functions being added together, you just add together the limits, the resulting limits. The third property that we looked at was a situation where you have the two functions being multiplied together. So if we have something like x approaches a of f of x times g of x, as we saw in the earlier example written in green, you have the result from the first limit, in this case it's defined as L, times the result from the second limit, in this case it's defined as M. Okay, so there's the third one. Now, the fourth one, let's take a look back up here. You may or you may not recall what the fourth one was, but the fourth one dealt with having a constant times the function. So what I'm going to do down here now is for the fifth one, we're going to do this limit as x approaches a. C is some constant times f of x. If you'll recall, we went ahead and we computed the limit of the function, which would give us the L, and then thereafter we just multiplied by C. So the result is like that. The fifth property we looked at had to do with division. If we do the limit as x approaches a of f of x divided by g of x, okay, you can reference back to the original problem that we did as an example for this. We evaluated the limit of f of x and we got L, whatever the numerator is headed toward, okay, or converging on. And then we evaluated the limit of the denominator, which was converging on m. So you just take the one limit divided by the other limit. The very last, or the sixth of these properties, was the property that says if we have x going to a of f of x and we raise it to some power, n can be any number you want. It can be a fraction. For example, a third would be a cube root. So it can be any power you want it to be, but what you do first is you evaluate the limit. Now, if we evaluate the limit of f of x as x approaches a, remember we defined earlier that we're going to get the value L, and then thereafter we can apply the exponent to that. Okay, so that's got that. These six properties are very important for evaluating functions. Let's take a look at something like this. Let's say you have something like the limit as x approaches -1 of the function x squared plus 6x minus 3. To evaluate this, you might just say, well, gosh, that's real straightforward. It's a quadratic, so it's a parabola, it's a continuous function. Okay, it's a polynomial. So all I have to do is plug the stuff in. Okay, so I'll take this -1, square it, plus 6 times the -1 minus 3, which will give us 1 minus 6 minus 3, which looks like it's a -8. Okay, and that's fine. But realize that in the process of doing this, we have used several of the properties 1 through 6 that we discussed above. First off, this first term in our function is actually raised to an exponent, which really says you just take the result and you raise it to an exponent, the appropriate exponent, and there we go. The second term in this, 6 times x, is actually a constant times the function. Okay, so I'm actually here going to reference the fourth property, which says I'm just going to take 6 times the -1, and that'll give me my -6. And then the last term, well, gosh, that was a property? Yes, indeed it was. In fact, it's way up here at the top. Oh, yeah, that's right. If we do the limit of a constant, and -3 is a constant, we just get that constant back. So realize that even when you're evaluating something like a polynomial, you're applying multiple properties from this list of the 6 that we've used. With these 6 properties in mind, let's move into something a little more advanced. Let's take a look at evaluating limits with rational functions. Okay, so we're going to look at limits with rational functions. Now, at its very basis, every polynomial is, by definition, a rational function. You could have something like y is equal to x squared minus 4x plus 3. And you may look at that and say, well, that's not a rational function. A rational function has to include a fraction. Well, if you want to get picky, it is a fraction. And you might say, well, that's pretty feeble. You can divide anything by 1 and it doesn't change it, but now it's a fraction. Yeah. So in the strictest definition of rational functions, every polynomial and basically every function can be viewed as being a rational function. But what we're going to do is we're going to try and confine our definition a little bit more. For example, let's say we have something like this. Let's say we have the limit as x approaches 2, and let's say we have something like x squared plus 2x minus 8 over 3x plus 6. Using the properties above, remember that one of them talked about division. I think it was number 4 and number 5 right along in there. What we can try at first is just plug in the 2 and see what happens. So what's going to wind up happening here is we're going to have 2 squared plus 2 times 2 minus 8 over 3 times 2 plus 6. Well, okay, in our denominator, we've got 6 plus 6 is 12, so we're in good shape there. We don't have any zeros in the denominator. However, in the numerator, notice that what we have is 2 squared is 4, 2 plus 2 is another 4. Oh, we have 8 minus 8, which gives us 0 over 12. Now, people sometimes get kind of confused here and they're thinking, uh-oh, I'm not quite sure what to do here. But if you have a 0 in the numerator, it equals 0. And just in case you're scratching your head wondering how to get that, remember if we have something like 2, well, let's say 12 divided by 6 equals 2, we can then work backwards and say, the 2 times the 6 does give us a 12, so that's fine. With that same idea in mind, if we have 0 over 12 equals, if we have a 0 as the resulting value, it is true that 0 times 12 will give us back 0. So 0 is fine in this case. Suppose the limit's a little bit different. Let's say we have the limit as x approaches 2, and our functions are going to be something like x squared plus 2x minus 8. Hey, we've seen that before, over 2x minus 4. Well, if we try substituting in 2, we know the numerator is going to be 0. And watch this. The denominator is going to be the 2 times 2 is 4 minus, holy mackerel, we get 0 over 0, which is an indeterminate form. And the reason is x equals 2 is not in the domain of the function. Well, okay, that's fine. If we were trying to evaluate the function, we would go ahead and we'd say it's undefined. However, in this case, we are not evaluating a function, we're doing a limit. So what we can try is going back to a table where we set things up with our x, and we have our f of x. Now remember, this limit says we're coming closer and closer to 2 from the left and the right side. From the left side, we can get values of 1.9, 1.99. If we substitute 1.9 into our function, you wind up with 2.95. If you substitute 1.99 in, you get 2.995. And if you continue 1.999, what you wind up with is this is actually headed toward 3. Okay, so if we come in from the left-hand side of this, we're actually headed toward 3. What about if we come in from the right-hand side? Well, let's see, we could do 2.1 as coming in from the right-hand side. Then we can get a little bit closer, 2.01. And we can keep going, 2.001, stuff like that. If you plug these in, you wind up with 3.001. 0.005, then 3.005. And if you do 2.001, I suspect you've already guessed it's 3.0005. From the right-hand side, this thing's also going to 3. Well, wait a minute. You mean I can plug a number into a fraction, and if I actually am at the number, for example, 2, I get something like up here at the top, which is an indeterminate form. But if I do the limit using a table, I get a very different result. 3. Interesting. Keep in mind, when you're working with limits, if you get an indeterminate form like this, you may want to go back to checking it on a table. Okay. Lots of times you'll be able to, as we've done earlier, just plug the numbers in and whatever number comes out is your answer. 0 is a perfectly fine answer. Not a problem with 0 at all. 0 over 0, that's a problem. And when you run into scenarios like that, using the table function on your calculator is a good option. One last thing we're going to take a look at here with rational functions is, what about x going to infinity or negative infinity? Okay, well, let's take a look at something like this. Let's say we have the limit as x approaches infinity. Now, the catch here is you don't have infinity that you can plug into a table, so we're going to have to figure out a different strategy for computing this. Let's say we have something like x squared plus 4x minus 12 over 3x squared minus 8x plus 11. And you're asked to evaluate this. Well, up to this point, the strategy would have always just been first substitute in the number and see if the algebra works. You can't plug in infinity. What we're going to wind up doing is we're going to rewrite this function a little bit. We're going to rewrite this as a limit as x goes to infinity. And I'm going to save some space here. I've got my x squared plus 4x minus 12. And in the denominator, I have this 3x squared minus 8x plus 11. What I'm going to do is in both the numerator and the denominator, I'm going to look for the highest power of x. Well, in the numerator, the highest power of x is this x squared. In the denominator, it's also x squared, so it's a tie, which is perfectly fine. What I'm going to do is I'm going to use the function written out to the far right, and I'm going to divide each term by the highest power of x. Both the numerator and the denominator, every term gets divided by the highest power of x. Okay, so we've done that. Where does that get us? Well, what we can do now is we can think about what would happen as the x values get really big. Our first, let's see here, our first term right there is x squared over x squared. Well, that's just going to be 1. So we're going to have 1. Then for our second term, the 4x over x squared, the denominator is going to get big much faster than the numerator. So as that denominator gets bigger and bigger and bigger, you have things like 1 over a million, 1 over a billion, 1 over a trillion. 1 over a trillion is basically 0. So the second term here is going to be going to 0. And for the third term in the numerator, 12 over x squared is going to be things like 12 over a million, 12 over a billion, 12 over a trillion. That's going to 0 as well. So if you'll notice, as x gets really big, essentially the numerator is going to a value of 1. We're going to do the exact same analysis in the denominator. For the first term in the denominator, we have a 3x squared over x squared. Well, the x squareds cancel, and guess what you get? You get 3. For the second term, we're going to have the 8x over x squared. You can cancel an x, so you have 8 over x. Now 8 over a million, 8 over a billion, 8 over a trillion is going to 0. Then for the third term, we have 11 over numbers that are getting really big. So 11 over something that's getting really big is 0, and this evaluates to be 1/3. So what winds up happening here is you want to acknowledge that you are integrating, that you're evaluating the limit as x goes to infinity. You look through every single term, numerator and denominator, and you choose the highest power of x. Divide everything by that highest power of x, like what we did over here in the upper right corner of the screen, and you evaluate each term one at a time to get a final result. Try this one. Let's say we have something like this. We have the limit as x goes to infinity. And what we have this time is something like 4x plus 8 divided by, let's say, x squared plus 6x minus 9. If you want, use this strategy that we just used in the problem immediately before this, where you find or identify the highest power of x, divide everything by that, and then evaluate term by term by term. So pause your computer, give this a shot, see what you come up with. Okay, so hopefully you actually paused and gave it some thought. Even if you didn't get an answer, that's fine. You gave it some thought, so you'll be a little more prepared for what we're going to talk about now, because you've probably thought through some of the things that we're going to talk about. In the numerator, the highest exponent is just x. In the denominator, the highest power is x squared. So the winner is going to be the x squared, and we divide everything by the x squared. Both numerator and denominator, each term gets divided by the x squared. Then, just as we did in the previous problem, term by term by term, we're going to look at each of these and say, okay, where is this going as x goes to infinity? Well, 4x over x squared is really just 4 over x. So that's 4 over a really big number. So that's really headed to 0. Plus 8 over a really big number is headed to 0. So that has both terms in the numerator done. Now, in the denominator, the first term, you have x squared over x squared. Well, anything over itself is just 1, except for 0 over 0. So that's just going to give us 1. Plus, now we have 6 times x over x squared, and x will cancel. This will give you 6 over x. So this term right here will simplify to be 6 over x. We've got 6 divided by a really big number. That's going to go to 0. Minus, then the 9 over x squared, yeah, that's headed to 0. And it's perfectly fine for the numerator to go to 0. The denominator goes to 1. 0 over 1 is 0, and 0 is a perfectly fine number. Okay. There's a third scenario that can play out. This is a limit as x goes to infinity. And let's say we have something like x cubed minus 11 over 5x squared plus 6x minus 3. As we've done in the previous ones, you look both numerator and denominator for the highest power of x. In this particular problem, the highest power of x is the x cubed here in the numerator. So what we're going to do is we're going to divide every single term by that highest power of x. So we have x cubed over x cubed, 11 over x cubed, 5x squared over x cubed, 6x over x cubed, and then this 3 over x cubed. And as we've done in this several problems that we've looked at up to this point, we're going to look at each part one at a time. X cubed over x cubed is just 1. So we have 1, and then we have minus 11 over x cubed. As the x cubed goes to infinity, this is going to wind up being a 0. Now take a look at what happens in the denominator. On this first term, you can cancel out an x squared, and this gives you a 5 over x. Well, if we have 5 over x, and x is going to infinity, it's going to be 5 over a million, 5 over a billion, 5 over something really big, and we get 0. Plus, the second term is going to simplify, and this is going to give us 6 over x squared. Just like the previous term, you've got a number, a constant, divided by a number. It's getting huge. It's going to 0. That's kind of a funny looking 0. Minus, and then this last one, 3 over a super huge number, that's going to 0. So what we wind up with is 1 in the numerator, 0 in the denominator. This is undefined. It is completely legit in this course to identify something as undefined if it is. Anytime you get 0 in the denominator, you're in trouble. Okay? In general, let's take a look at what's going on here. In general, okay, if you have a situation where the degree of the numerator, the degree talks about the highest power, is equal to n, and the degree of the denominator is equal to m, some other thing, like the numerator could be x squared and the denominator could be x cubed. So you would have a degree in the numerator of 2, a degree in the denominator of 3. 3 things can happen. First off, if n is equal to m, in other words, they are both the same value. Let's take a look at something like that. Let's say we have ax to the n plus bx to the n minus 1 plus, and this continues all the way down to something or other. Okay, let's say k over. Now let's say we have something like dx to the m plus e x to the m minus 1. So we're just lining things up so that the exponents decrease one step at a time. So x cubed, x squared, x, and then just a constant. Let's call this p. Okay. If n equals m, the limit is x goes to infinity of the numerator's function divided by the denominator's function. Now remember, if they're tied, okay, these two are going to be the terms that are left standing, and the x's will cancel. Now, if the x's cancel, what you're left with is the coefficient in the numerator divided by the coefficient in the denominator. We saw something like this earlier in our very first example. Okay, it's the one at the top of the screen. Notice in this first example, it says x squared in the numerator, but there's understood to be a 1 there as a coefficient, which then leads to the 1 in our numerator for our final answer, and then the 3, which is from the denominator, lands right there. Okay, so if they both have the same degree, if it's a tie, you just take the coefficient off of the numerator's leading term divided by the coefficient off of the denominator's leading term. Second thing that can happen is n can be smaller than m. If we do the limit as x goes to infinity of this f of x divided by g of x Now, what's going to happen here is, remember, the exponent in the numerator is smaller than the exponent in the denominator. We've already looked at a case like that. That's the one that's at the top of the screen now. We had the 4x plus 8 divided by x squared. And remember, we wound up with 0 in the numerator and some number in the denominator. It can be 1, it can be something else. But when you have 0 over some number, you get 0. The third thing that can happen is n can be greater than m. Then if you evaluate this limit as x goes to infinity of f of x over g of x equals, we did one of those as well, where the numerator had the higher power. Okay, that's now at the top of the screen. Remember, we had the x cubed minus 11 divided by 5x squared. So we wound up dividing each term by an x cubed. Got some number in the numerator divided by, and the denominator was 0. Well, when the denominator is 0, you're done. This is undefined. These three properties are very important to keep in mind and make life really easy. For example, let's say we have something like the limit as x goes to infinity of 3x squared plus 6x minus 2 over 8x squared plus 7x plus 12. First thing I do is I notice, hey, we've got a tie. X squared in each of them. If there's an x squared or the same power of x is the highest power in each of them, you just pull off the two coefficients from those leading terms and you're done. It is literally the case that on limits going to infinity, if you have a rational function and you have these three properties in mind, you can look at it and go straight from looking at it to writing down an answer. Be sure that you practice a number of these in the homework. These are pretty straightforward once you get the hang of them.